At 09:42, every dashboard was green. Checkout was already failing. One payment request reached a healthy service, crossed the load balancer, and then waited at the database. The architecture looked serious. 2 availability zones, auto-scaling, a multi-AZ database, alarms, and backups. The labels were correct. The behavior was not. The hidden problems were not the AWS services by themselves. They were the assumptions between them: paths, signals, budgets, retries, recovery, monitoring, and restore proof. A normal review could have approved this design. It had multiple zones, managed entry points, an elastic application tier, a managed database, alarms, and recovery artifacts. That distinction matters. The load balancer still routed. The app task still responded to health checks. The database failover mechanism existed. Some parts were doing their job. The gap was behavioral. Nobody had followed one real transaction through degraded latency, scaling pressure, retries, failover, monitoring, and restore evidence. A senior review changes the lens. It asks how a critical request behaves when one dependency becomes slow, unavailable, overloaded, or recently failed over. The application did run in 2 availability zones. On the diagram, the system looked symmetrical, but resilience is about every dependency on the transaction path. When the request needed outbound access or a downstream dependency, one shared route became the real failure domain. The architecture was multi-AZ at the app layer, not across the whole path. This is why a resilience review follows the path, not the boxes. If one concentrated dependency disappears, the remaining zone may still be unable to complete checkout. The control is not more decoration on the diagram. Align dependencies by zone, or use a regional design that is intentionally resilient, and test the transaction path during zonal impairment. The servers were not busy. They were waiting. CPU stayed calm while checkout latency climbed, because threads and connections were stuck behind the database. A better scaling signal represents the work customers are waiting for: request count per target, queue, backlog per worker, concurrency, or a service level latency budget. When scaling follows the wrong signal, the fleet may scale too late, scale in the wrong direction, or add workers that only increase pressure somewhere else. The production control is a scaling contract. The metric, the target, the warm-up behavior, the maximum fleet size, and the condition where the system stops accepting more work. The application tier could add capacity in seconds, but each task carried a connection pool, so scaling the fleet also scaled pressure on the same finite database. The review question is simple and often missing. Maximum tasks multiplied by pool size equals worst case database concurrency. If nobody owns that number, nobody owns the blast radius. Connection pooling or a proxy can help by sharing connections and protecting the database from sudden surges. It still needs limits, queue behavior, timeouts, and monitoring. A production design sets pool limits per task, maximum service scale, database capacity assumptions, shedding behavior, and an alarm on saturation before checkout turns red. Every timeout looked like a failed request to the caller, so the caller tried again, while the original work was still running. One payment path became duplicate work. Retries belong inside a budget, maximum attempts, exponential backoff, jitter, idempotency, and a point where the system fails fast instead of adding more load. Then the database failed over. That does not mean RDS failed. The managed service can move the primary, while application connections still point at the world that just disappeared. The control is an exercised recovery path. Short DNS caching where it matters, reconnect safe pools, tested failover drills, and customer latency measured during the event. The load balancer was healthy. The application health endpoint was healthy. The database was available. Checkout was still broken because none of those checks bought anything. The useful picture combines traces, metrics, logs, and synthetic transactions. Traces show where req7f21 waited. Metrics show saturation. Logs explain the local failure mode. In the reconstruction, customer support saw the pain before infrastructure alarms did. That is the monitoring smell. The business signal arrived before the operational signal. The control is a customer journey objective. Synthetic checkout, real user signals where appropriate, trace coverage, latency and error, budgets, and alarms that page on impact. The architecture had snapshots. That is good. But a snapshot is not the same as a restored service, with networking, identity, secrets, configuration, and dependent applications working again. A real recovery review starts the clock. Can the team restore the data, attach the right permissions, redeploy the service, validate checkout, and do it inside the promised window? RTO and RPO are promises. The evidence is a restore test result. What recovery point was used, how long the restore took, what validation passed, and what failed. The production control is periodic restore testing in a safe account with validation steps, deletion rules, documented gaps, and an owner who closes the recovery defects. The repaired architecture is not just more AWS icons. It is the same customer path with resilient dependencies, demand-aware scaling, bounded concurrency, retry budgets, recovery drills, journey monitoring, and restore proof. Run req7f21 again. This time the system either completes the checkout inside the service objective, or sheds work deliberately before it harms the database and the customer queue. Before calling an AWS architecture production ready, ask 7 questions: paths, scaling signals, connection budgets, retry safety, failover recovery, customer monitoring, and restore evidence. The professional question is not, does the diagram look production ready? It is. Which assumption would fail first if this request met real pressure tomorrow?